Welcome to qnawire.
So we're considering a simple model for a power transfer in an inductive charger. So we have within a charger's plastic base a primary coil that has a diameter d, and a value of little n sub p. This is the number of turns per unit length in the primary coil. And it's connected such that there's a current running through it, which has some constant value, times the sine, times the sine of 2 pi ft. So this is a time-dependent current that has some frequency f. So when the toothbrush is seated on the base of the coil, there is an n-turn secondary coil within the toothbrush, represented by the red bit here, and it has capital N total turns. We're supposed to find an expression for the EMF induced in this secondary coil. So, noting that the B field from the primary coil is given by mu naught little n p times the current going through it, which is I naught sine 2 pi ft, and using the fact that the area of the subcoil, the smaller coil here, is simply going to be given by pi r squared, where r is just the diameter divided by 2, we can write an expression for the induced EMF. So the EMF induced is given by negative the change in magnetic flux through the subcoil per unit time. So now we can differentiate our expression for the flux with respect to time. We see the only time-dependent component comes from this sine term. So when we differentiate this bit with respect to sine, we know that d sine of 2 pi ft with respect to time is simply going to be 2 pi f cosine of 2 pi ft. So plugging this in for the induced EMF, we find an expression of minus 1 over 2 times pi squared times diameter squared times the frequency times the total number of turns in our subcoil times the number of turns per unit length in our primary coil, all times I naught cosine of omega t. And this whole expression is our final answer.